In this video, we will be talking about the properties of aromatic compounds, including their physical properties and their chemical properties. This is to build upon our learning objective for describing the bonding in benzene and understanding what differentiates an aromatic compound from an alkene. If we are going to compare the physical properties of aromatic compounds to similar cyclic alkanes and alkenes, we find that the melting point for aromatic compounds is much higher. And this is due to the fact that the benzene rings are completely flat. And so a horizontal view of this ring looks somewhat like this. I'm just trying to try out the back atoms here. They are completely planar, flat, whereas the alkanes, cyclic alkanes, are not flat. You can see the bonds here are alternating up and down due to the tetrahedral bonding arrangement around the atoms. Each atom here is essentially trigonal planar geometry, which means it is planar. Since they can stack together very closely and tightly, there are stronger dispersion forces between molecules of benzene than there are between molecules of cyclohexane. So, fewer dispersion forces. They can only contact each other in a few discrete spots versus these flat molecules where they can attract one another in multiple locations. So, much more dispersion forces. More packed. And you can see that in the melting point here. This is a negative melting point, and then this one's finally something that's above 0. The reactions of aromatic compounds are also much different than our regular alkenes. We talked earlier about how alkenes can undergo addition reactions such as halogenation in order to form alkanes that are substituted. But if we try to do the same to our benzene, there's no reaction. The aromatic nature of the benzene makes it more stable, and so it's more resistant to the chemical reactions that break it up. We can still do reactions with our aromatic compounds. It just takes a little bit of extra work, and we can see that the products are different than a normal alkene. When we did our addition reactions earlier, then we ended up with 2 chlorines on our structure. In this electrophilic aromatic substitution, we are substituting rather than adding. We are removing 1 hydrogen and then putting on 1 chlorine. Nitration also removes 1 hydrogen and then adds on an O2 group. This hydrogen here was color-coded blue, and on the product side you can see that that is bonding to the chlorine. And similarly, this is going to leave behind 1 O and the H, and that can go with the blue hydrogen here. Sulfonation does include H2SO4 as well, but what's getting added on is SO3, sulfur trioxide. So here's a practice problem for you. What would be the product of the reaction shown below? Go ahead and pause the video and try to think about this. Unpause the video when you want to check your answer. So when we have this adding to benzene, this is going to be a substitution reaction. That means we're going to be removing 1 hydrogen, and that's going to leave as a byproduct. And then we're going to be adding an O2 onto that. And if we do a little bit of subtraction here, And then we know we're adding on NO2. That's going to give us 1 oxygen left over and 1 hydrogen. So that's going to bond over here. That's going to make water as a byproduct. So we are looking for C6H5NO2 as our product.